Uh, Welcome back. So we still have. So we've proved the lemma. Let's see. I'm sorry. We showed how the lemma gets used. Okay. So now we need to prove the lemma. So again, the lemma will work in finite or infinite groups, but you may want to think of the finite case. It's more elementary. Given f and L2 of G, define capital F is going to be a mapping from G to L2 of G. So as I promised you, a mapping from the group to a Hilbert space. In the finite dimensional case, it's just from G to Rn. And how is capital F defined? It's defined by spinning little f around. So capital F of x is defined as little f of gx. G ranges over G. Okay, so again, I have to take an element of the group, which I call x, and map it to a, not to a real number, but to a vector. So this is the vector that I get. I take the function little f, and I have the vector f of gx when G ranges over G. Now let's consider the random walk xt. Xt is the random walk. We're going to start it as some specific vertex x0, which could be the identity, but it doesn't really matter. So let's compute the norm in L2 of G. So this is a random variable, so I want to compute its expectation. So this is the expectation of the sum. So let's write explicitly what is this norm. We have to sum over G and G, little f of xtg minus little f of x0g. What? Sorry, f of little x is this mapping. This is defined for any choice of little x. F, capital F, is a map from G to L2 of G. X sub t, okay. Thank you.
Are you assuming G is Abelian?
No, not at all. So, yeah, no, that's a good point. We want to keep this. So, and there's a square. And also, since G is not abelian, we have to keep track what is this random walk. This is the right Cayley graph and the right random walk. So xt plus 1 is xt times, maybe I'll write wt plus 1, where, so each time wt plus 1 is a random neighbor of the identity. So it's a random generator. So we evolve in the group by multiplying by random elements from the right. And G is acting from the left. It's kind of unfortunate, but we have to keep track of the directions here. So we have this expectation, and the point to realize is that this is as a, so how can we write this? So as G goes over the group, I mean Gx0 also goes over the group. So I want to now Gxt is the same as the result of the random walk after t steps starting from G. So I can write this as in the following form. It's the sum over x, y in G, f of y minus f of x squared, p to the t of xy. So the point is you think of this as x, and then this, you call this point y. And in the expectation, you will just get pt coming as ptxy. So this is just writing out what this expected sum means. So here we have a double sum. We're summing over both x and y. And you see that this is going to be very close to the Dirichlet form. So let's write it out as sum, fx squared plus fy squared minus 2 fx fy ptxy. Okay, now remember that we are doing a simple random walk on a group here. Pxy is symmetric. Pxy is the same as pyx. It's just 1 over the degree if they're neighbors and 0 otherwise. So if I take this sum and break it up into the components, suppose I just look at the contribution of fx squared. When I sum over y, I'm just going to get the sum of ptxy over y is just 1. So this is going to be, the first term here is just the inner product of f with itself. The second term is exactly the same, because ptxy, if I sum it over x, I just get 1 for each y. So I'll just get the sum of fy squared, which is give me another product here. And the interesting term is this one, which is exactly the product of pf with f. With a factor of 2, thank you. I missed the 2 before. So 2 times the inner product of pf with f, or f with pf. Minus, thank you. This is exactly twice, and there's a p to the t here. This is twice the Dirichlet form. Okay, look at this formula for the Dirichlet form. It's exactly twice what we have there is twice the Dirichlet form. Okay. So we're going to use this calculation twice. There's no inequality here. All this was exact identities. So first, let's use that for t equals 1. For t equals 1, I claim, if I do, for any x0, and for any y which is a neighbor of x0, if I want to look at 1 over d times f of y minus f of x0 squared, and observe that this is less than the expectation of the norm of f of x1 minus f of x0 squared. Here I need a norm. Because if I compute this expectation, remember x0 is just little x0, it's the same. If I compute this expectation, well, one of the terms, x1 is a random variable, uniform over the neighbors of x0. One of the choices is this y, and the choice y has a weight of 1 over d. So this is just a sum of positive terms, and one of them is this term. So that's why this inequality is certainly true. But this is what we calculated here. So this is twice E1 of f. So we can rewrite this as a form. So fy minus fx0 norm is going to be bounded by a square root 2d E1 of f. Now this is true for any two y and x0 which are neighbors. So this really gives me a Lipschitz constant for this mapping. So now I claim that from this I can deduce that for any y and z, say, in the group, if I look at f of y minus f of z, look at the norm of this, it's bounded by this this constant, root 2d E1 of f, E1 of little f, times the distance in the Cayley graph from y to z. Because what is the distance from y to z? Just the length of a path. For any two neighbors, I know that the norm of the difference f of x0 minus f of y, if they're neighbors, was bounded by this constant. So this really gives me a Lipschitz, that the function f is Lipschitz, f of y minus f of z. I just write it as a sum along the path. Maybe I'll spell this out. So if y, maybe y1, y2, up to y rho equals z. So this is the path going. So I start from y, which is y0. This is the shortest path, and its length is rho, which is the distance. And then you just use the triangle inequality, fy minus fz. This is less than the sum f of yj minus f of yj minus 1. J goes from 1 until rho. Rho is, I'm going to abbreviate just for this calculation, rho of yz, I'm calling it rho. So and here I have the norms. So I just use the triangle inequality for the norm. Each of these terms, well, yj and yj minus 1 are neighbors, so this inequality applies. And so by just adding these up, we'll get this bound. Okay? So f is a Lipschitz embedding, capital F is a Lipschitz mapping from the group with its graph metric to the Hilbert space, which is, finite or infinite dimensional Hilbert space. Okay, so now we want to use that once again, use this inequality. The square is got erased here, or never got written. So this is the square norm. Yeah, this is the square. Okay, so now we want to use this identity for a larger t. So what can we say about this sum using what we just verified here. So I'm going to continue from this quantity and say this is at most the expectation of this constant. So fxt minus fx0 I can bound as follows: root 2d e1 of f times rho of x0 and xt squared. Well, all of this is squared. Right, so the norm is just bounded below, I'm sorry, the norm is bounded above by this quantity. Okay, so we get, this is bounded by so this is at most 2d e1 of f. Well, this is equal 2d e1 of f times rho of x0 and xt. And now we're done. We just have to compare the two sides. Rho squared and expectation. Thank you. Okay, so now we've proved the lemma. Just compare. Here we have the expected rho squared multiplied by this constant, 2d(e1f), and here we have 2etf, right? So divide both sides by 2d(e1f), and you'll get the 2 cancels, and you'll just get this inequality that was stated here. Okay, any questions? Yes?
Is f of capital XT like a martingale or a 2D?
So, not exactly. It's very close to a martingale. So, but to get a martingale, you actually have to scale it by lambda to the, multiply by lambda to the minus t, and you'll get a martingale. So one can recast this, one can rewrite this argument using martingales, but in this case it doesn't make it shorter, but it is actually useful if you want to go further. So here I bounded from below the distance from the distance squared from x0 to xt, the expected square distance. Often you're interested to bound the distance, not just the square. Now, if I were to try and apply this argument directly, I bounded from below the square distance, and this is going against the Cauchy-Schwarz inequality. So I cannot directly infer a lower bound for the first moment from a lower bound for the second moment. However, using this remark, because we can relate it to a martingale and then use what's called the Burkholder-Davis-Gandhi inequalities, one can actually get from the second moment to a first moment bound. And the details are in this paper with James Lee that I mentioned. And we also have a follow-up with James Lee and Charles Smart that's available on the archive, which will also to appear, where we have more precise probability bounds. So one thing you might want to say, not just that the moments are large, but really that the distance is typically large. So the probability that xt and x0 are closer than epsilon root t should be small. So refinement of this bound, it says that the probability that the distance from x0 to xt is less than epsilon root t, this should be small, this should be like order epsilon, provided t is not too large, and so t is not too large, so t should be still less than the relaxation time, and epsilon is not too small. Epsilon should be bigger than 1 over root t. And such a bound, I'm not giving exactly the conditions, but such a bound you can find in the work with James Lee and in a follow-up paper I wrote with James Lee and Charles Smart. But this is more details than I want to present here. Let me mention one mystery.
One question.
Yes.
When you said it's a martingale, that was specifically for the second eigenfunction.
Yes. Sorry, thanks. Yeah, so we saw that the optimal choice of f is the second eigenfunction, and so to get a martingale, we apply, we multiply by lambda to the minus t. In the infinite case, one has to do something different. So one can make f actually into a, in the infinite amenable case, you can make f to be a harmonic embedding into Hilbert space. And then you don't need, so, but this requires further argument in the infinite case. All right, let me mention, so in the finite case, we have this inequality, right? So we had the inequality, was bigger than, in the finite case, we had 1 over 2d times t over 2d for t less than t rel. Okay, let's. I'll copy it on the top. So for the finite G, what we showed is that expected rho squared x0 and xt is going to be at least t over 2d for all t less than the relaxation time. So really, for all t up till 1 over 1 minus lambda 2. Now, applying this, okay, so one question is, can this bound be extended a little further? Obviously, this bound cannot hold forever, because if we're in a finite group, rho is bounded, so we have to stop sometime, but does a bound like this hold all the way until time which is t mix? We don't know. So does it extend maybe with different constant until t mix? This we don't know. But just using, it certainly doesn't extend with this proof. So for this proof, the function f that we chose is the optimal function, and it really works until t rel. But we don't know if the inequality itself can be pushed further. Using the inequality we just verified, so this is a lower bound for the rate of escape. Let's use it for the largest t we are allowed, namely t rel. So what do we get for, so for t rel, here we have this distance. Well, this distance is certainly at most d squared, most the diameter squared. So we get the diameter squared is at least t rel over 2d. Okay, so here, this is some bound. This is some expected distance squared. It's certainly bounded above by the diameter squared. This is bounded above by the diameter squared. And this is, so I apply this at t, which is t rel, and use the fact that this is at most diameter squared. So we get this bound. Okay? So this is the bound I promised before. The relaxation time is at most diameter squared times degree. And here we got a 2. This kind of bound was actually proved earlier by Babai in 91, I think, is the first one to prove this kind of bound using a completely different method, which didn't. So here we got some more information. We got information on the distance at all times at most t rel, but just this fact about the spectral gap can be proved in other ways. So this reproduces a bound of Babai. The constant t2 here can be reduced to 1, but it's not so important. And one consequence of this is the mixing time is at most 2d squared times, well, constant doesn't matter, d times log n. So remember, we had a bound relating mixing time and relaxation time. It said T mix is at most Trel times a log of 1 over epsilon pi min. So because we are in a Cayley graph now, pi is just uniform. So pi min is 1 over n. So we get a log n here. So diameter squared times degree times log n. Open question, can you remove the log n? So this is a conjecture I made a few years back. So diameter squared times degree, in fact, for any transitive graph. So let's talk about lazy, simple random walk on any transitive graph. Again, going from T mix to Trel, you have to worry about, from Trel to T mix, you have to worry about periodicity. So again, the safest thing is talk about the lazy walk. And then all the eigenvalues are positive. Okay, so for lazy simple random walk, I conjecture that this is true. We don't know any counterexample, but we don't know any improvement on this log n. So be very happy if someone solved it. I've tried a few years. And I've pressured my students, but they all found other problems to solve. So that's open. Now, let me. We have until when 11 and 11:30. Okay, so I want to tell you one. So those of you who have background in algebra can think of lots of interesting groups. For probabilists who are not algebraists, the most useful group beyond the lattices and free groups is the Lamplighter group. So a quick survey. Who's seen the Lamplighter group before? Please raise your hand. Okay. So a minority. So, so let me tell you what these are. So it is... Okay, so people here with background in algebra this group can be constructed as a wreath product, but for us what is important is actually not the group as an algebraic object, but the Cayley graph. So I'm going to focus on describing how does the Cayley graph of this group look. This is, the best way to do it is first describe what is an element of the Cayley graph. So now I'm talking about the Lamplighter group, and let me start with the Lamplighter group over Z. So there will be, this Lamplighter group will have a base, and so the Lamplighter group over Z looks as follows. This is an infinite group, but we'll shortly modify it to get finite groups. So what is, I'm going to draw in this picture not the Cayley graph, but an element of the Cayley graph. One element looks as follows. On the integers, we have lamps that are on or off. So on is indicated by 1 and off by a 0. But we have only finitely many on. So we have a sequence of zeros and ones with only finitely many ones. And we also have a marker or lamplighter at some integer point. So this picture is a picture not of the Cayley graph, of one element of the Cayley graph. It consists of a vector of zeros and ones, finitely supported, so only finitely many ones. And so an infinite sequence of zeros and ones, but with only finitely many ones. And a marker pointing to a specific integer. This is an element of the graph. I have to tell you what are the neighbors of this element. So the neighbors of this element, it has 3 neighbors. One is obtained by moving the marker to the right, another by moving the marker to the left, and the third neighbor is by flipping the lamp at the marker. So I can change this 1 to a 0, and that will give me my third neighbor. Okay? So again, the graph has this infinitely many vertices. When I change the lamp, the marker stays in place. So again, the configuration consists of this lamp configuration and the marker. The neighbors are three neighbors. One is move marker to right, don't change lamps. Move marker to left, don't change lamps. Or keep marker in place and flip the lamp. So this is, it's called the lamplighter group because it describes the motion of an imaginary lamplighter who, at every step, he decides, will I move right, will I move left, or will I flip the lamp where I am? And this is one move. Okay? Now, this is the lamplighter when the base graph is z. But this definition makes sense for any base graph. So if we want a finite, so this is lamplighter group over z. We sometimes denote it as z with a picture of a lamp here. But you could have a lamplighter over the cycle. So if I take z mod n, the lamplighter over that just consists of a cycle with n nodes. And here we have lamps. And we have a marker somewhere. And more generally, we could take any base graph. In applications, we usually want base graph itself to be a group or transitive, but you could really take any base graph you want and think that's the graph where the lamps are sitting. And on this graph, we have lamps that are on or off. And the marker is sitting at some node of the base graph. And he can move to a neighbor in the base graph or flip the lamp where he is. So for any base graph, there is a corresponding lamplighter graph, which is much bigger. So if we start with a base graph of n nodes, then the corresponding lamplighter graph will have n times 2 to the n nodes, because we have all the configurations of lamps and the locations of markers. Now, this graph has dead ends. So let's look at a configuration like this, 1, 1, 1, 1, and here is, the marker is here. Okay. What is by the way, the identity of the group turns out to be when all the lamps are off and the marker is at the origin. Okay. So suppose this is the origin, and I'm in such a configuration. So I have a sea of ones around me, a block of ones, zeros outside, and I'm exactly at the origin. The marker is at the origin. Okay. Now,
your graph is transitive.
My base graph, yes, in the examples, you could make this definition more generally, but I'm focusing on the transitive case. So now look at the case when the graph is z. So this example, so the base graph is z. And I'm looking at specific configuration, which looks like this: marker at the origin, block of ones centered at the origin, everything else is zeros. Now, if I'm in this configuration, what steps take me closer to the origin? How do I get back to the identity in this graph? Well, I need to turn off all the lamps and get the marker back to the identity. So when I'm here, there are many paths that get me to the identity. I could turn off the lamp where I am, and then move to the right, turn off all these lamps, then move to the left, turn off all these lamps, then move the marker back to the origin. Or I could also, it would be equally efficient to take the marker, move it all the way here, and only then start turning off lamps. So from this configuration, any step you take actually gets you closer to the identity. So this configuration is a dead end, and it's quite a deep dead end. It will take you, if you want to get from this starting point, you can calculate the distance to the identity. And if you want to get to a point further, you have to actually first get quite a bit closer to the identity before you get further. It's really a strange situation, but this is a Cayley graph. And the same thing still holds if instead of z, I wrap this around and this is happening on the cycle. So also this is a finite group with dead ends. So random walk and mixing time on these groups is quite interesting. So for instance, so if I'm on this group, the lamplighter over Zn, it has if I'm in this group, even though it has, maybe I'll start in the infinite case. This group has exponential growth. So if I am going into distance n from the identity, I can certainly turn on any lamps that I want, say in the n over 2 steps to the right of the identity. So that shows you the ball of radius n has a size at least 2 to the n over 2. In fact, the ball of radius n has size which is the golden mean to the n. That is the right order. The Fibonacci numbers come in. But so G has, so the lamplighter group over Z has exponential growth. Yet if you look at the expected distance from x0 to xt, it is only growing like constant root t. The reason is that as we start with all the lamps off, the marker at the origin. The only lamps can turn on where the marker is. The lamps can't turn on, it doesn't have a remote control. So the marker is just doing a delayed simple random walk on the integers, right? He's walking on the integers with some laziness of 1/3.
Okay. Questions, comments? Oh, sorry.
Yes.
Question, what is the group operation in this lamplighter?
So, all right, given two configurations, you hear me now? Is this better? Yes. Okay. Given two configurations, what you do is the way you look at their product is you say we're in base group is Z. So then we just add the locations of the mark. So the new marker will be the sum of the two markers. The lamp configuration is more sophisticated. You don't just add the two configurations of the lamps. You take the second configuration and you shift it by the marker of the first, and then you add it mod 2 to the first configuration. Okay? So this is known as a wreath product in algebra. But for analyzing random walks, it's not really needed, but that's the group operation. Again, if you look up lamplighter groups, you'll find information, or wreath products, you'll find information. In particular, in my book with Russ Lyons, we have a lot of discussion of lamplighter groups.
So at some point you said that the diameter of a group is bounded by log n.
The diameter of any graph of bounded degree, So because if the degree is d, then in k steps you can only reach d to the k vertices. So in order to reach n vertices, d to the k must be n, which gives k, which is log n to the base of the degree, or d minus 1 in fact. Yes? So it's just a class of examples, but I wouldn't call them anomalies. They are, because it's not just one example, it's a whole class. And it's interesting because you can create one for any base graph. You can create a lamplighter graph. And the lamplighter group can illuminate the original group. So, for instance, you can ask, given an infinite group, I build the lamplighter group on that. When does the random walk on the lamplighter group have positive speed, escape at linear rate? And the answer, if and only if the base group is transient. So if I look in ZD, random walk in ZD always has 0 speed, but we know it's transient in dimension 3 and higher, and recurrent in dimension 1 and 2. And if I do the lamplighters, they will have, the lamplighter we talked about in dimension 1, it has speed 0, or distance is only root t. In dimension 2, it turns out that the distance is t over log t, because the range of a simple random walk in 2 dimensions is t over log t. So if you ask, by time t, how many different nodes does a random walk in 2 dimensions visit? The answer is order t over log t. And that corresponds to the distance that the random walk in the lamplighter group will travel. And if we are in 3 or higher dimensions, then the lamplighter, the walk in the lamplighter group escapes at positive speed. So these are, it's a very interesting class of examples. There are other important classes like Glauber dynamics on Ising models, one of my favorite things, which I don't have a chance this course to discuss.
Majid?
So you have given example of getting different constants. So first lamps are indexed by 0, 1, switch on and off, and the next step you are considering integer line, and next step you said that replace lamps by lamplighter group itself. So is it possible to get some different constant if I say consider the base group as some group, and at each point I am instead of switch on and off, I am considering different group whose cover time is say higher.
So what happens if you change the base group? Okay, the question is, are we looking at infinite or at finite groups? So here I was emphasizing. So for finite groups, it's more complex story. But for infinite groups, really, there's if the group is one-dimensional, if it's z or a small variant of z, then simple random walk goes distance root t. If the group is two-dimensional, then simple random walk already visits t over log t versus, so already the exponent is 1. And once you are at 3 and higher, then the range grows linearly, so the lamplighter group will have positive speed. For groups, there's this wonderful classification based on Gromov's theorem. So Gromov's theorem tells you that groups of polynomial growth have a very simple structure. They're all finite extensions of nilpotent groups. So they all can be essentially written as matrix groups. And this means that you cannot have, for instance, a group of polynomial growth which grows like, where the balls grow like r to the 2.5. It has to be an integer power, and random walk on any group of integer growth behaves roughly like random walk in ZD. So this means that for the purpose of obtaining different exponents, there is really, you have to keep the base to be Z. But the lamps, you can be more creative. But then, this is just one class of constructions, the lamplighter groups. There are much more elaborate constructions that people have done. So if you want to see, just open this paper of Bruxelles and Zhang or Amir Virag, and you'll see some really beautiful constructions that at least make my head spin.
Or glow.
Yes.
The base graph is so it's not the case that the lamplighter group is also a
No, it's not the case. So, so I said what is the group of Z is abelian, but the group operation is not symmetric. So when you add, I said you take the configuration of the second lamp and you move it by the first marker, and if you do it the other way, you'll get a different configuration. So it's not abelian. And so, infinite, finitely generated abelian groups, it's very restricted. They have polynomial growth. So the Lamplighter group is a finitely generated group. So we just have, say the Lamplighter group over Z, you just need 2 or 3 generators. If you want a symmetric set of generators, just 3 generators. And it already has exponential growth. It's impossible for an abelian group with 3 generators, you will have structure, a growth 2 or 3, at most R cubed. Anything else? Manju? Can you speak louder?
So, in the infinite case for these proofs, are they completely different or how
So, lemma, but there you have to distinguish the amenable and the non-amenable case. In the non-amenable case, there's a different argument that says the random walk escapes at linear speed. So, in the amenable case, you can use a similar argument, but you don't have eigenfunctions in general. You have but you can use the spectral theorem for self-adjoint operators to use use approximate eigenfunctions in a very similar way to what I used. Or you can also use the function f to be the number of visits in a Fellner set. So you take a Fellner set. So a Fellner set is a very, very large set whose boundary is relatively small, like a box in ZD. So amenable groups are defined by the property that there exists very large sets where the surface to volume ratio goes to 0. And if you take such a set, this is called a Fellner set, and define f of x to be the expected number of time, the expected time you will spend inside the Fellner set, then you can plug this f into this lemma and use that. So there are 2 options for which f to use, and again that's discussed in the paper with James, and also we added that to chapter 13 of the book with Russ. You can find that there. Yes?
2 questions. One is there some reason why epsilon is taken to be 1/4 as a convention? And more than that, is it always the case that for the analysis you take epsilon to be independent of n?
So, okay. So, conventions are by definition things that don't have a good reason. That's why we say it's a convention. But the point is, a half is really a crucial watershed. So, if you take something like the example I showed several times, 2 complete graphs with an edge between them, then if you take any epsilon bigger than a half, then T mix of epsilon will be order 1. Within a constant number of steps, 1 or 2, you get within a half of total of stationary measure, because you completely mix inside one side. But to get below a half will take a long time. So any epsilon less than a half is good as any other epsilon. So we have to choose some number less than a half. A quarter is a reasonable choice, but some people have used 1/e or 1/2e.
And is epsilon always taken to be independent of n?
No, but this turns out to be the most useful point of view. But again, I stated in the first lecture that classical point of view was to fix n and let epsilon go to 0. So really try to understand how fast you go to very, very close to the stationary distribution. Of course, you could let both n tend to infinity and epsilon tend to 0 and study that case. And so some of the bounds I wrote, I wrote T mix of epsilon, and then we have dependence both on n and on epsilon. But if epsilon tends to 0, very fast, then what you get is basically the relaxation time multiplied by log of 1 over epsilon. So it's not as interesting. Yeah, the lemma is for an infinite graph also, that's right. It's in the application of the lemma. The application of the lemma used so the lemma is true for an infinite graph. The question is, how do you derive the theorem from the lemma? So for that you have to choose a good f. So one method is to use spectral theorem for self-adjoint operators. So because you no longer have eigenfunctions, but the spectral theorem gives you approximate eigenfunctions, and you have to use spectral project. So if one knows the spectral theorem, it's easy to take this proof and build an analog in the infinite case. And there is also another construction of f, which is more geometrical, using Fellner sets. That's what I. But the lemma was very general. It's just the application of the lemma. That's it. People are hungry.
No other questions? So there are posters downstairs. Please go and have a look at them.